welcome, and we're back section 1.3. We're going to talk about functions and relationships and what they mean, how they go together. We're going to find out that the function is a specific type of relationship. What's a relation? It's just something that's related between two numbers. It's an ordered pair. Those things that we talked about in that section 1.1. Okay. So let's get started. Let me get clicked over here. So what we're going to do is we're going to look at things. What is a relation? How does it is a relation a function? So everything is going to be kind of a relation, and then a function is going to be a very specific. And then we're going to be learning about notations we use. Why are they special? Okay. And then this determine the domain and range of a function. We have to go through and develop them for several different types of functions as we go. Okay. So what is a relationship a function? Okay, well, what the heck is a relationship? Okay, so the definition of a relation is just a set of ordered pairs. So remember, this is kind of what we're thinking about so far, is that if I went and graphed something on a coordinate system, I've got some points. So if I went out here on my number line, 1, 2 for my x-axis, 1, 2 for my y-axis, and I just did a point, that point was 2, 2. It wasn't the old, 2, 2, 2 less than x less than 2 interval stuff on this doesn't even make any sense here. But if I had something like -2, 2, it wouldn't be the -2 to 2. Okay. So it's not that is not an interval notation. We're going to kind of mix these things in together, and unfortunately, we need to be very clear about whether this is a coordinate point, a point with coordinate 2, 2, or is it some type of interval that we're talking about. Okay. So this set of ordered pairs, what is an ordered pair? An ordered pair is just something x, y, 1, 2, 3, 4, a pair of numbers, and the order matters. The ordered pair, so this is not equal to 2, 1. Okay. So the order matters. 1, 2, 3, 4, I can have an order paired 1, 2, 3, etc. But the order matters. Okay. Usually we think of x's as coming from some set, x from some set. Maybe some set A, 1, 2, 3. And the y's are from some set. Let's say B, and that is 4, 5, 6. Okay, this is the domain. This is the domain of the x's. So this is the x values. And the range is the y values. Okay. So we could build up a set of ordered pairs. So the ordered pairs would be like 1, 4, 2, 5, 2, 3, 6. We could do 3, 6 or 2, 6. Some set of pairs where the x's are from here, the y's are from the second set. So what about a function? So all of this that I build up is a relation, okay? Anytime I do this is just a relation. I've got a relationship between the two. There's a relation there, okay? But now a very specific thing is a function. And functions are what we are going to, everything, and functions are just this big classification. But we're going to study specific types. The quadratic, you remember that? The polynomial functions, so quadratics are polynomials, linear functions, absolute value functions, radical functions. Those things that we kind of looked at before, we're going to look at it in terms of two variables, and they're going to look kind of familiar to us. Okay. So the function, though, this is the definition of a function, is that given a relation in x and y, I have an ordered pair x and y. The only time that I can use a function notation, so all of this was a relation, yes, because I have an ordered pair, but a function is a very specific, okay? It's a very specific relation. And the way I identify is I go through, right now the way I go through is I look for each value of x, and there can only be exactly one value of y in the range, okay? So here's a table. We've got some little rule, right? The rule x squared plus 1, 2x minus 5. There is some rule that exists, and we've generated some x, the inputs from the domain, to the outputs y through that rule, and these are the range. So here's the domains, here's the ranges, and what we're going to do is look to make sure that we don't have any value of x going to two values, okay? So 3 goes to -4, -2 goes to 0. Here's the ordered pair, 3, -4, -2, 0, 5, 3, 1, 0. So I see each one of my x's only listed one time, and they only go to one individual output. So if I had 3 going to -4, 3 going to 0, that would be a problem, and it wouldn't be a function. Okay. So why functions are so important is because they are the things that are most useful in life. There's a lot of other things that are useful, okay, but the general things, so if I'm in engineering, I use functions, everywhere. And here's kind of the concept of why functions are important. I have a drink machine. I've got a little button. I call it button A, button B, button C, right? I'm going to put, like, here's my dollar that I put in here, and then I get a particular drink down here at the bottom. You've probably seen these things. It's a drink machine, okay? Now, as long as I do something like this, I can assign any drink. I can put drinks in here, and I can say this is what you're going to get. So as long as I get something like this, so here's a big solution set, right? I get, well, if you pick A, you're going to get a Mountain Dew. That's fine. B, you get a Pepsi. That's fine. This could have been A, Pepsi, B, Mountain Dew. C, well, we didn't have any other drinks, so we can get a Pepsi. This is fine, okay? But I've got them labeled up here. You go in, you put your dollar, you hit button A, you get a Mountain Dew, you know what you're getting, you're good. You go put your dollar in, you select B because you wanted a Pepsi. Maybe this one was out, but you see I've got another Pepsi here, so I select C, I get a Pepsi. Everybody is happy, okay? This is a good function. I know what I selected, I know what I get out, everything is fine. Chugga chugga chug. Engineer B, that was engineer A. Engineer B comes up with this. If you select A, you get a Mountain Dew. Well, okay, if you select A, you might get a Pepsi. This is a relationship, just two things, ordered pair, right? And then a B is a Mountain Dew. So what is the problem? I go stick in my money. I say, okay, I want a Mountain Dew. I punch the button A. Sometimes I get a Mountain Dew. Sometimes I get a Pepsi. I don't even know what probability it is. Is this most of the time? Is this some of the time? It's just up in the air. And this is not a function. It is a relation. Is a relation. So a relation is any type of these things, two things going together, okay? It is a relation, but it is not a function. It is not a good engineering piece. There's no, when I do a throttle, I don't want to have, sometimes I go 20 miles an hour, sometimes I go 5 miles per hour, sometimes I go in reverse. Man, that is no kind of engineering there at all. So mostly engineering, when you're doing your analysis, you're thinking a function, and it is just a general way of doing a mathematical relationship with a very specific property that when I hit one input, I get one output only. Okay, so that's what this would be a good function. Okay. So here, what about these things? I can do this question in several different ways. Here is a set. Here's my set 2, 3, 2, 4, my set of sets 2, 3, 2, 4, 3, 5. So here's the things that I've got. If I do this, look here, I've got a 2 and a 3 and 2 going to 4. Different wise, the same x. This is not a function. This is a good relation. Determine if the relation. This is a relation. Everything is fine. I'm not worried about anything. But when I think about it building this, now I put my $2 in, sometimes I get Mountain Dew, sometimes I get Pepsi. So how about this one? 1 goes to 3, 2 goes to 3, 3 goes to 5. Now this is okay. If I select 1, I get my Pepsi, 2, I get my Pepsi, I know exactly what I'm getting. 3, I go and get my Dr. Pepper. Okay, I've got an overload where a lot of people get Pepsi. Sometimes I run out. So either one of these, I'm going to get a Pepsi, and that's going to be fine. This is a function. It's certainly a relationship. This is certainly a relationship, but this one is the only one that is a function. Okay, so here's another quick one. 8, 4, 3, negative 1, 5 to 4. Each individual x goes to a particular y. That's fine. If I had 8 going to 4, 3 going to 4, 5 going to 4, that's fine. But we know what we're getting output when we get the input. Okay, we can have a constant where everyone goes to the very same thing and it's still a function. Okay, negative 3 goes to 2, 9 goes to 5, 1 goes to 0, negative 3 goes to 1. Well, which one? If I give you the negative 3 as my input, there's my throttle. Do I get 20 miles per hour or do I get 10 miles per hour? Does it jerk back and forth? What does it do? This is not a good function. It's not things that we would use in engineering. So a very different notation. Let me open this thing up. Hold on. Put this out here. Okay. Let me go back. So here's a different notation. Here's the sets. Okay, so this says I start with my x. This is kind of like a machine. Here's your inputs. The x's are your inputs. So in general, a function has inputs and it goes to outputs. Okay, inputs are my throttle selection, outputs is how fast I get. Okay, inputs, I select the button on my transmission, park, reverse, neutral, drive. My output is what I do when I do that thing. And I'm good as long as if I put it in park, I don't go to drive, right? Park, drive is a problem. Okay, so here's my inputs or my x. These are the inputs. All of this stuff is the input. And it's like a big domain. So all of this is the domain. I have some function. Okay. Here's some general function. I'm going to use this notation, and it goes to the range. Okay. And the way these things are doing is saying, I've got negative 2 going to negative 2. 6 goes to 6. Pi goes to pi. And what it looks like is this is the identity function. It just y is equal to x. 1, 1, 0, 0. And I'm just going to use a little different notation, but that's the functional notation is give me 0, 0, 1, 1. I don't have to square it. I don't have to do anything to it. Okay. But this is the domain. That's the range. And is this a good function? It's a relationship. So this thing would be listed as these particular ones, negative 2, negative 2, 6 to 6, and then pi goes to pi, okay? So that's our set notation from this, and it's certainly a good function because each one only goes to one output as far as what they can give me, so that is a good function. Relationship, yes, relationship is that big thing. Okay. Determine if the relationship defines y as a function of x. So for any particular value, I multiply it times the number times 2, okay? And then I'm just going to add 6. Is it a function? Yes, because I'm going to get a very specific thing. When I do this calculation, I'm always going to get the very same thing. I'm not going to get a second thing. So it's a function. You know, I'm not going to say 1 this time as well. That's going to be 2 times 1. And then the next time at this is 1. I'm going to say 3 times 1. This is well-defined set of operations, and I get the same output. Very same thing here, even though I square it. No matter what I do, I get that one particular output. I do this one particular number, times 2 is a particular number, and it's not every time I get a different number. Okay, so both of those are going to be functions. Okay, again, order of operations, these are fine. Now this here would be fine. Now, if I'm looking at this, I can actually look at it 2 ways. I can have this function of y. As a function of y, this is good, okay? But what about if I say so this x is a function of y, but is y a function of x? So if we did what we did in review chapter, if I solved for y in terms of x, I would get to this y squared, subtract the x, I get my y squared is equal to 7 minus x, take the square root, and remember I always drill, take the plus and minus of these because there's 2 solutions. Now it's not a function. Well, which one is it? I've got 2 outputs for that 1 input. So this is not a function. It's a good solution to this. We're not talking about really solutions. We're just talking about using a mathematical model and being a good mathematical model. I would have to limit this. I can limit this thing to a particular side, either plus this version or minus this version, but I need to always have the same thing as an output. Okay, so all of those. So what about if I have a graph? Is there anything I can do to look at a graph and tell if it's a function? And there is. It's called the vertical line test. I want to back up now once you've seen that. So a graph defines y as a function of x if no vertical line intersects the graph in more than one point. Okay, so they've got that simple picture here. I've got a circle. I've got this circle, and if I do this vertical line or this vertical line, I see it cuts that place there and there. So for one x input, there's my x, I get 2 different values of the y. Okay. So if I go back and if I look at graphing a straight line, any x, I get 1 output. So this is a good function, okay? A quadratic, when we start graphing that y is equal to x squared plus 1, you remember when we did that? When I went here, if I pick an x, if I draw all the bunches of lines, there's no place that when I get an x, I get 2 different outputs like that circle. Now before, I had that x is equal to something like 7 minus y squared or something. Anyway, if I have something like that, it turns out to be graphs look like that, which is a good graph, no problem with it, except when I'm giving you an input, and this is kind of what we want to be able to do is do analysis on it. Then every time I do this, I've got a problem. I've got 1 version, 2 versions. Do I have 3 versions? Does this turn back into look something like this? And here for 1x, I have like, 1, 2, infinite number of y values. And which one do I use? So that becomes a problem. That standard, this basic analysis that we're going to do with these functions are not going to work. So not a function. Okay. And this thing that I'm doing, drawing a line, is called the vertical line test. Vertical line test. This is the VLT. So that one is a function. There's a couple of lines drawing down each one of those, and it has to be every line possible. So if there's some place that it folds back over where you get a problem, that it cancels out for everything, okay? Here's one where it goes up, and then it comes right here. And I've only got 2 points. I don't even have any extra things right here, but I've got a closed point here, a closed point there, okay? then it's not a function. So this, I got two closed points. For this x input of 0, I've got a y is equal to, looks like 4 and 1. Well, which one? Well, sometimes this, sometimes that. So this isn't, but what I can do is say I'm going to limit this thing so this is not real. So that hole says that x0 is the one that's filled in, it's not that one, and it turns it into a function just by doing that. So any overlap is what this is doing. As let me kind of do another picture. So they will show you some graph. I've got some good graph that goes here. You know, vertical line test is good. But then, so at the end, maybe this is 2. Now, once I get past that, I'm using this graph. So that works, that works. This has to be open. That has to be closed. I got a big smudge there now, and it looks like it. Okay. So this is a good function. Okay. All right. So let's go through, we'll kind of look at these things. This one, if I drew a line over here, I would cut it at 2 places. So this is not a function. This looks like a good function. Here, I've got these both closed in dots. So if I drew, every place looks good, except this right in here. And if I drew that line at -2, what would be the output? 2 or 4. So I'd have to open that up. So that way it is not a good function. Okay, a different way, here's some x's. They're all going to 4, 2 to 4, 3 to 4, 8 to 4. This is a good function. I know exactly the output that I'm getting. So I could actually have this is called a constant function, x, y. So this is like x, y equal to 2. So here at 1, it's 2. At 2, it's 2. It's 3, it's 3. But I'm only going, I know exactly my output that I'm getting is y is equal to 2. So this is a constant function. And it looks like whatever the value is at this x is still going to be 2. And it looks like if I did that, y is equal to 2. This x squared plus y squared is equal to 25. If I went to Desmos, that would graph out to be a circle, and then it would cross out just like it did before with that circle. This, kind of trust me or go to Desmos, check Desmos. I think you would get here to be, here's 5, 5, -5, 5. And I think this thing would be a circle here, and this radius would be 5. Okay, so check that out on me. That's kind of one thing that you can do. And this would be the problem. So any place along here where I touched, I would have 2 outputs for this one input. Which way? So not a function. Not a function. Why? Fails VLT, the vertical line test. Yeah. So the functional notation is just a way to, number one, instead of having to write the rule every time y is equal to 2x squared minus 3y, I can do this and say this is which one I'm talking about. So I can actually have different things. Okay, so I'm using f of x, but that's the most general thing. So let me kind of open this thing up and let me kind of give you the idea. Okay, I can have different names and use this function notation. So I can have f of x is equal to 2x minus 1 for a particular thing, right? G of x is x squared plus 2. H of x is 3x cubed plus 2x squared minus x. Okay. So when I'm talking about functional notation, this is kind of the general, most general notation. F of x is when I'm talking about a general function, but this is saying g is a function of x. I'm calling this rule g, this rule h, this rule f. Now I could go back, this would be problem 1, and then problem 2, I can say, well, f of x, now for this analysis, you're going to use x minus 1. G of x, 2x. R of x. You know, I can have h of x here, r of x down here, and not even have one thing. So I could have a mix, right, is equal to 2, the constant function. And then I'm going to refer to find f of 1. What is the value of this function at 1? Oh, it's 1 minus 1. That would be 0. What is g of 1? Oh, that's 2 times 1. That's 2. What's r of 1? That's 2. That's always going to be 2. R of 5 is 2. R of 6 is 2. But f of 6 would be 6 minus 1 is equal to 5. Okay? So that's the notation. So this is evaluate the function. That's what that means, evaluate the function. If I just say f of negative 3, that just means evaluate that function as negative 3. I don't need this big evaluate. F of negative 3, the value of the function at negative 3, evaluate f at negative 3. There's several different interpretations, and you kind of use what you need, but that's basically stick that negative 3 in there, do the negative 3 in here, and do the calculation through calculators. Here is evaluate f at the square root of negative 2. What is the value of the function at the square root of square root of 2? 2, square root of 2 squared minus 3 square root of 2, plus 1. Do your simplification what you can, and then this would be the exact form of the solution. Sometimes it just goes to a different variable. So I could start out with one variable. This is called change a variable. Okay, so I have some function, f of x is x squared plus 1. I can change, so basically I'm saying let a equal to x, and then I want to evaluate that. So I'm going to use this in here. That's just a squared plus 1. And now you got to give me the a. Okay, I can do other things. I can do, using f, evaluate f of x minus 1. So I take whatever's in there, whatever in here, put it in where the x was the holding spot. So I would just go x minus 1 squared plus 1. So there's a lot of good uses for this that we can do. We're going to learn about these and doing this as a transformation. This is going to slide this graph over by 1. And we'll look at that as we go forward. But these are more, here's some skill practice. Determine x and y intercepts. So later as we go to graph, we're just going to be basically saying where I want to do some graphs, some general graphing. Okay, I'm going to know somewhat the shape based on its form. We're going to look at that. But I want to know, like in general, it's going to increase, it's not going to turn back over, it wouldn't be a function. I want to know these two things. Those are very useful things to put on a graph. Here, not so much. We want to know, we do the calculator version or interpolation, But here, this is the x-intercept. This is the y-intercept. So we got the x-intercept and the y-intercept. And how I find this is I set f of x equal to 0 or the y equal to 0. So if I'm thinking of, let's go, y is some function of x, right? And here's my rule, x squared minus y. And if I want to find the x-intercept, I set y equal to 0, so I solve this. So that would be the graph. This would be a quadratic, and it would be up here. Okay. The y-intercept, this is easy, always easy. I just set x equal to 0. And since I'm using functional notation, that is just f of 0. So for this, f of 0 would just be 0 squared minus 1, which would be just -1. It would be down here. Okay? But that's how I find the y-intercept. This is the y-intercept. So let me see if there's any other good things. We're going to go back over this as we go through. I just want to get through most of this stuff real quick. Determine the domain and range of the function. So the domain, that is the x's, okay? The range is the y. If I'm looking at a graph, I just read off in interval notation. So we're back doing interval notation as a mix here. Okay, so for that graph right there, we're going to assume all of R. It looks like it continues on. So the domain, I'm going to use that domain big symbol, is just -infinity to infinity. Give me any x and I'm going to be able to do the calculation. This is that all of R. This is what we're going to assume when we're doing functions. Assume. Okay, and then the range, well, I can assume, but can we do better? Okay, so here I can say -infinity to infinity, but it's actually better. So here it looks like 2 to infinity. So here, if we do better, it's 2 included all the way up to infinity. And I'm basing this on, well, this looks like a 1, 2. If it went from 2, then it's going all the way up. Okay, that value. Okay, so that's the basics of that. We'll go through and look at some more examples and continue on.